In this video, we will learn to mesh the car using Fluent meshing. Firstly, we will create a surface mesh on the car, then we will create boundary layers around the car, and finally we will learn to create a polyhex core volume mesh. Go to Properties, then make sure Workflow is highlighted and Watertight Geometry is selected as shown. Double-click to open the mesh. Polyhex core meshing is parallelized, allowing you to create a mesh faster on multiple cores. To enable this, select Parallel and insert the number of physical cores available. Import the linked geometry. Enable local sizings. Pick point near field from the zones. Add a local sizing, choosing body of influence under the size control type, and having 16 mm as target mesh size. Name this local sizing as boy near field and add the local sizing. Pick both the rear and front wings from the zone labels. Add another local sizing, choosing curvature and having a 0.5 mm size and 12 mm as max size. This will allow areas of high curvature like the leading edge to be appropriately refined. Name this curvature wing and add the local sizing. There are other local sizings created similarly. Please make note of the mesh settings as we go through them. A body of influence for the far field, having 64 mm as the target size. A curvature for the rods with 4 mm size and 16 mm as max size. A curvature for the wheels with 16 mm size and 32 mm as max size. A curvature for the chassis with 8 mm size and 32 mm as max size. A curvature for the wheel radii with 1 mm size and 4 mm as max size. Have 0.5 mm as min size and 256 mm maximum sizing. Input 3 cells per gap to resolve small gaps and to obtain a good quality volume mesh. These settings will dictate the global parameters. Create the surface mesh. Insert a clipping plane and inspect the surface mesh. The mesh settings captured all the features accurately, but, in your case, additional local sizings may be required. This geometry has only fluid regions and no shared topology. Under Boundaries, change the boundary zone of the sky to symmetry as we do not want boundary layers forming on the sky, and update boundaries. This is just a temporary zone change and will be changed back to wall in the solver. There are no changes to be made here, so update the regions. The prism settings are crucial in capturing the boundary layers, resolving inaccurate pressure coefficients. Use a Y+ calculator to guess the first layer. Additional mesh refinement studies are required to understand the number of layers required. Generally, for an Y+ of 30, 5 to 10 layers is a good starting point. For this simulation, the last ratio method was used to create prisms. A total of 6 layers and a transition ratio of 0.2. Input a 1 mm first cell height. More info about the different methods and variables can be found in the help. A link to how to access the help is added in the description. Change the fill to a polyhex core mesh, and create the volume mesh. We can visually inspect the volume mesh created. We can see the boundary layers at the rear wing. This shows the boundary layers between the wheel and the ground. We can save the workflow, meaning all the mesh settings will be saved and can be recreated later on. The mesh is ready to be taken into the solver. Thank you for watching. In part 3 we'll cover solver settings.